Good morning, sir. And our project is design and analysis of highly isolating mega antenna for wireless applications. In this project, we are discussing about MIMO antenna. The main agenda of our project is to provide isolation between two patch antennas. So for this isolation, we are using 5 metamaterials. The frequency operation for these two antennas is about 5.2, 5.8 gigahertz. It is in C-band applications. CHT software is used for simulation reports. The main objectives to calculate for this is gain, diversity gain, low envelope correlation coefficient, high isolation, low VSWR, the realized gain, high efficiency, low return loss. The main MIMO antenna is for transmission of high data rate. MIMO antenna is nothing but combination of two or more antenna elements. The main application for this MIMO antenna are Wi-Fi, wireless low area networks, and for mobile communications also. In this project, we have taken references from the Neeraj Kumar, Ashok Ahmed, Suzian in the years of 2018, 1920. Neeraj Kumar is the main taken EBG, electromagnetic band structure. In his proposed methodology, he used to tell about metamaterials. And 2019 paper, he mainly discussed about 5G applications. And 2020, he mainly told about 2x2 MIMO antenna, mutual coupling reduction.
Now we are using CST software. The software is more advanced model in this project generation. We using the CST software, we can measure the parameters of the structure of in this antenna. Design parameters: return loss, gain, diversity gain, analog correlation coefficient, VSWR, insertion loss, efficiency, and realized gain, surface current distribution, and radiation value. The first one is return loss. When we transmit a signal, it will be reflected back, and the reflected time is loss of information. That loss of information is called return loss. Next one is gain. In which direction the antenna perfectly work or good accuracy. In which direction the antenna good accuracy is called gain. Diversity gain. Fading effect will occur in this diversity gain. The fading means the noises in this present atmosphere or external signals, noise will be occur. We have to remove that fading effect. We are use diversity gain. Next one is analog correlation coefficient. It is the radiation pattern of one antenna. It depends upon itself. That does not impact the other radiation pattern of the antenna. It is called analog correlation coefficient. Next one is voltage standing wave ratio. The VSWR is defined as the amount of mismatches that occur between the antennas.
Insertion loss. The amount of power lost during the signal's journey from transmitter to receiver is known as insertion loss. IL is equal to minus 10 log PL by PN minus 20 log root over PL by PN. Next, efficiency. Efficiency is calculated by dividing the entire amount of power radiated at the output and the amount of power radiated at the input. That is ER T radiated by T input. Next, realized gain. There is a chance to get realized gain whenever the antennas have two ports. Realized gain is 5 times the radiation intensity to the incident power of the antenna. Surface current distribution. Surface current distribution is defined as occupying the maximum amount of current over the entire surface. Current distribution is only achievable when an electric field is applied rather than magnetic field. Next, radiation pattern. The radiation pattern is a pattern that is created when the energy released from the antenna is measured in terms of pattern. It can be explained in two ways: near field pattern and far field pattern.
Is coming to see our antenna design. Here we are designed our antenna with a size of 37 into 44 mm scale. Here we are using FR4 substrate because it has very less cost. Our entire antenna is working at a frequency of 5.8 GHz frequency. The dimensions of our metamaterial unit cells is 5 mm width, 4.2 and 3.5 are the external lengths. This is our proposed antenna construction and geometry. This is the structure of our proposed antenna. These are the specifications and dimensions which we are using to design a proposed antenna. This is our antenna with dimensions and specifications. Coming to results, we obtain the antenna parameters with the help of the CST simulation software tool. Here, computer simulation technology is used to run and simulate our antenna, our desired antenna. Here we obtain several parameters like ECC, DG, return loss, and efficiency, insertion loss, realized gain, VSWR, and surface current distributions are at different values. First, coming to envelope correlation coefficient. In our proposed project, we got envelope correlation coefficient value is 0.002. Next, coming to antenna efficiency, we got antenna efficiency is 99%. Here, we obtained the return loss is minus 18 dB. Here, we got insertion losses minus 24 dB. In realized gain, we got 4 dB gain. Diversity gain we obtained in our proposed project is 9.99 dB. Here we obtained gain at two ports, port 1 and port 2. Here port 1 we obtained the gain is 2.88 dB, and at port 2 we got the same gain at 2.88 dB at port 2 also. Here surface current distributions we are obtained at two ports, port 1 and port 2. Here the surface current distribution at port 1, and this is the surface current distribution at port 2. These are the E fields. E field patterns at port 1 and port 2. This is the E field at port 1, and this one is E field pattern at port 2. This is the radiation patterns we are obtained at port 1 and port 2 with an angle of theta equal to 0 degrees and theta equal to 90 degrees. This is the graph for radiation pattern at port 2. We are obtained at theta equal to 90 degrees. This is the comparison table which we are compared our proposed project with our base paper. We are obtained very far and good results better than our base paper. These are the few references we are taking to design our proposal project. This is our the software we are using to design our project. This is the CST software, means computer simulation technology software. We are going to use our designed antenna. So here we designed 4 components: component 1, component 2, component 3, and component 4. Here component 1 we discussed about port 1. Here component 1, here it contains 4 points. First one is core. This is the core. Second one is feed line. This is the feed line. Third one is sheet. This is the sheet which is outside of the core. This is the Teflon which is present inside the sheet. And component 2 we are placed about ground. And component 2 we placed ground and substrate. This is the ground and this is the substrate. And component 3 we discussed about the second antenna. So this is the core. This is the feed line. This is the sheet, and this is the Teflon. At component 4, we discussed about output ring. That is, this is the output ring is completely discussed about the metamaterial. These are several groups that we are using to simulate our project. These are the materials. Here we use the copper material. This is the copper. This is the FR4 lossy metal. This is FEC. This is PTFE, which we are going to use with Teflon. These are some of the curves. These are ports, port 1, and this is port 2. Here port 1, we give the input at port 1, this here, and this is the port 2. We are give the input to the at port 2. These are field monitors. Here field monitors, it consists of E fields and H fields. Our entire antenna is working at a frequency of 500 GHz frequency. Here the H field at 500 GHz frequency, E field at 500 GHz frequency. This is the far field at 500 GHz frequency. This is the controller which we are using to design our project. These are the graphs we are obtained at 2 ports. With respect to port 1, we are with respect to port 1, we are explaining port 2. With respect to port 2, we are explaining port 1. These are the different port signals we are obtained in this project. Those are the S parameters. This is S11, which we are representing the return loss at 500 GHz frequency, as we are mentioned here. We obtained the return loss at minus 18 dB. This is S21. Here is the insertion loss. Here we obtain the S12 with respect to second port. Here S22 with respect to second port. These are the references impedances which we are obtained at port 1 and port 2. At our reference impedance is 50 ohms. These are the balance graphs to balance our two T-shaped patch antennas. Here the two powers, excitation power 1, excitation power 2 means at port 1 we are obtain the power at port 1 and we are obtain the power at port 2. These are the energies. Energies are obtained at port 1 and energy obtained at port 2. These are two energy graphs. And these are the materials as we are discussed in previous copper, FR4 substrate and PET substrate. These are the materials only. And this is the distance effective directly constant like line impedance. These are the different parameters which were obtained. Here we got the efficiencies. Here we got efficiency at two ports, port 1 and port 2. Radiation efficiency at port 2, total efficiency at port 1, total efficiency at port 2. This is the VSWR value. We are obtained at port 1 and port 2. This is the VSWR value at port 1. This is the VSWR value at port 2. We are obtaining the same value in those two ports. This is the port E field. E-field current distributions. Here current distribution is obtained at different frequencies. This here we are designing the different frequencies, but we are calculated and read the value at only the 500 GHz frequency only. This is the far fields. This is the far field at port 1. This is the far field at port 2. These are different far fields at absolute radio, theta phase, and phi phase. These are the different radiation patterns. Finally, we have got a realized gain at 4 dB at 500 GHz frequency. This is the diversity gain. This is the correlation coefficient. These are the some of the parameters which we are obtained by using the CST software in our project. Thank you.
Thank you.